Good evening, students. In the previous video, I have completed up to the phase of the simple harmonic motion, and also I have told that I will continue with the velocity and acceleration part. So, today I will continue with that. Okay. So, let us begin. What do you mean by the velocity? The definition is same, that the rate of change in displacement with respect to the time is the velocity, right? So, here also for the SHM, that is simple harmonic motion, the definition of the velocity will remain same. So, the rate of change of the projection in with respect to the time is called the velocity of the simple harmonic motion. Now, we have to find out the expression of this velocity. Okay. So, let us see how we can capable to find it. So, for the in, that is for the projection, the displacement y is given as a sine omega t, right? So, therefore, what will be the velocity? V is nothing but dy dt. Already we know it from the 1D in motion, right? Differential form of velocity. So, instead of y, we can replace it by this d dt. Now, a is constant. What will be the differentiation of omega t? Sin omega t, that is will be nothing but cos omega t. For sin omega t, the differentiation is cos omega t. Sorry. So, for sin omega t, the differentiation is cos omega t. Now, omega t is another part. So, for this omega t, the differential will be omega. So, the expression, final expression will be a cos omega t. Okay. Hopefully, it is clear to all, right? Now, so this is the expression of V. Now, what we can write instead of omega t, cos omega t, what we can write? We know that sin square omega t plus cos square omega t, that is equal to 1. So, cos square omega t nothing but 1 minus sin square omega t. Again, cos omega t is nothing but under root of 1 minus sin square omega t. Now, what is sin omega t? That is y, right? So, what we can write? We can write 1 minus y square by a square. If we simplify this part, 1 by a root over of a square minus y square, right? Hopefully, it is clear, cos omega t, the value of cos omega t. Now, come to this side. I am removing this part. So, V equals to a omega cos omega t, right? What will be the value of cos omega t? That is 1 by a root over of a square minus y square. Just replacing the value. A cancel out. So, V becomes omega into under root of a square minus y square. So, this is the expression for the velocity of SHM. Okay. Now, the velocity of the particle in SHM changes with the displacement y of the particle. When the displacement is 0, suppose if y equals to 0, then what will be the velocity? So, velocity will be omega into a, right? And if that is omega equal to y is, that is velocity will be the maximum, which defines that at the equilibrium position, the velocity will be the maximum for the SHM, right? Now, if what will be the velocity 0 if suppose if y becomes a. So, if y becomes a, then the velocity will be 0. So, this is the condition for maximization of the velocity and this is the condition for minimization of the velocity. Okay. Hopefully, it is clear to all. Now, coming to the acceleration of SHM. Now, what do you mean by the acceleration? Same thing that for the acceleration part, we all know that rate of change in velocity with respect to time is known as acceleration. Okay. So, same thing here there. What is A? A is nothing but dv dt. This is the differential form, right? So, now dv dt instead of v, we can write A omega cos omega t. Okay. So, A omega is the constant term, that's why I am making it out. Now, what is the differentiation of cos omega t? That is minus sin omega t. Now, omega t is there. So, for this omega will be the differentiation. So, the result will be A omega squared sin omega t, right? Now, what is this A sin omega t? That is nothing but my y. So, acceleration is defined as minus omega squared y. So, this is the expression of the acceleration and from this expression what we can conclude? We can conclude that the acceleration of the SHM is opposite to the displacement. Okay, in the opposite direction. Why opposite? As there is the negative sign. If omega square is constant, so we can say that acceleration of the SHM is directly proportional to the minus y. Minus y minus, here, from here we are getting minus, that's why the acceleration of n, that is the projection of the SHM, is proportional to the displacement of y and its direction is opposite to the direction of the displacement. Okay. Hopefully, it is clear to all. Next, I am going to the periodic time of SHM. Already, I have discussed that. So, let us discuss it once more. So, basically, the discussion will be depending on the terms of acceleration and velocity. Okay. So, all of we know that the time period t is defined as 2 pi by omega. And from the previous equation, what we got? We got that acceleration equals to minus omega square y. So, from here, we can find that omega equals to acceleration by y. Now, considering the mod value, that is, it considering the positive value of omega and under root. Okay. So, instead of this omega, if I put it here, so what will be the value of t? So, t will be basically 2 pi of under root y by a. So, this is another expression. This is one expression, general expression, and this is another expression of time period considering the acceleration and displacement. Okay. So, we can use this formula to determine the periodic time of SHM. Okay. Now, in the previous part, I have said that y equal to a sin omega t, right? And again, in the previous first two videos, I have discussed that according to the Fourier, SHM can be considered as the superposition of sine and cos, right? So, therefore, as I have considered the y equals to a sin omega t, we can consider as cosine as well. Okay, so let's see whether it is possible or not to represent the SHM in terms of cos. So, according to the previous drawing, I have considered P here. This is the theta and this is the projection N, right? So, if we consider this P, instead of doing this, if I consider this P as along this, not considering this, if I consider the theta here, then the terms, that is ON Y, becomes cos, right? So, therefore, we can write x equals to A cos omega t. Okay. So, what will, if I consider the displacement along the x, so what will be the velocity term? Let us discuss that. Same thing, velocity will be dx dt. A cos omega t, right? So, A omega will be outside minus sin omega t. Again replacing the values like the previous one, V will becomes basically minus root over of A square minus x square. And the acceleration will be, if I consider the acceleration, dv dt, A omega sin omega t, again minus omega square A cos omega t. What is cos omega, A cos omega t? That is nothing but my x. So, therefore, minus omega square x. So, look, the same expressions we are getting, just the changes, displacement is changing. Okay. So, this is the superpose. Again, we are establishing that the Fourier's statement is again correct, because from both of the part, that is from using the sine and cos, for both things we are getting the same expressions for the SHM. Okay. So, what will be the general representation of SHM? The general representation of SHM, if we consider the phase, then it becomes x equals to A cos omega t plus phi. Okay. What is phi? Phi is the initial phase. Okay. Now, what is the characteristics of linear SHM? The characteristics of first is that motion of the particle is in a straight line to and fro about a fixed position. This one, and the position, this is the fixed position which is called the equilibrium position. The restoring force or the acceleration acting on the particle is always proportional to the displacement of the particle from the equilibrium position, and this acceleration is always directed towards the equilibrium position. So, what does that means? This is the, so acceleration is always tends to in this position. That's why we are getting that minus sign. Okay. And so, according to these three characteristics, what we can say for as the definition of the SHM, The definition of SHM is that when a particle moves in a straight line to and fro about its equilibrium position in such a way that the force or the acceleration acting upon it is always directly proportional to its displacement and directed towards the equilibrium position, then the motion of the particle is called the simple harmonic motion. Hopefully it is clear to all. So, in the next video, I will continue with the differential form of the SHM. Thank you.